Hello everyone, my name is Prachi Garela and I will be taking your recitations for this course. Today we will be solving some practice problems from chapters 1, 2, and 3. And then when we meet on Wednesday, we will continue solving some practice problems for the midterm. Okay, so let's just start at any point if you feel that you have some questions. If you are watching this live, you can comment them or you can raise your hand. Or if you are watching the recorded version, you can just mail me or text me on Teams. Okay. So let's just start. I hope everything's visible. Let me make sure. Yes. Okay. So let's start with problem 1. Problem 1 is from chapter 1. I will keep mentioning which problem is from which chapter so that if you want to revise, you can look at those chapters. Okay. So the first problem is that the main span of San Francisco Golden Bridge is 1,280 meters long. At its coldest, okay, the bridge is exposed to temperatures ranging from minus 16 degrees Celsius to 38 degrees Celsius. The question is, what is its change in length between these temperatures? And you're required to assume that the bridge is made up of steel. Okay. So if you would like to attempt to solve it, I would suggest that you pause the video, try to solve it, and then come back and look at the solution. Okay. So the solution is, first we will look at the things that are given to us. What's given? We have the length, which is 1,280 meters. And we have the change in temperature, which is given by this range. So that is 54 degrees Celsius. And from your formulas, you know that to find the change in length, the formula is alpha L, which is length, and the change in temperature. And what is this alpha? It's the coefficient of expansion for steel. And for steel, it's 12 into 10 to the power of minus 6. And its units is per degree Celsius. Okay, so if we substitute everything, what you get is, so that's the alpha. L is 1280 meters, and the change in temperature is 54 degrees Celsius. So if you note here, we want to find delta L, so the units should be meters, which means since this is per degree Celsius and this is degree Celsius, these will get cancelled and you will indeed get a unit of meters. So this is a nice way to check that what you're finding out, it has the correct units. So this gives the answer to be 0.83 meters. Okay, that's good. Okay. So let's start with problem 2. So problem 2 is from chapter 2. Okay. The problem 2 is, suppose your bicycle tire is fully inflated with an absolute pressure of 8 into 10 to the power 5 Pascal. Okay. At a temperature of 22 degrees Celsius. The question is, what is the pressure after its temperature has risen to 38 degrees Celsius on a hot day? And you're required to assume that there are no leaks or changes in the volume. Okay, so again, I would advise you to pause, look at the question and try to attempt it and then come back for the solution. Okay, hope you're paused, and now here is the solution for you to check. So again, like last time, we will see what are the things that we already have. So okay, so let's see. So we are given the pressure at temperature this. So we will take this to be our initial pressure and initial temperature. Okay, so P initial is 8 into 10 to the power of 5 Pascal. Okay, and T initial is 22 degrees Celsius. We also have T final, which is 38 degrees Celsius. And another thing that we have here is given by this assumption that we need to assume that there are no leaks or changes in the volume. What this means is that Vi is equal to Vf. And now we will employ the formula that we know, which is Pi Vi over Ti is equal to Pf Vf over Tf. Let me write it in a better way. Okay, so now here, since these two are same, we can just cancel these here. Now we are left with Pi Ti equals Pf Tf. And if you want to find Pf, we can simply write this as this to give us Pf. Now we will simply substitute and get the answer to be, okay, before we substitute, we need to make sure that we change these temperatures into Kelvin. So how do we change? For 38 degrees Celsius, we just have to add 273. So this becomes 301 Kelvin, and this becomes 295 Kelvin. Okay. Now we can easily substitute, and the answer will be, so Pf is equal to 8 into 10 to the power 5 Pascal. And remember, we need pressure, so the unit should be Pascal. And the temperature is 311 Kelvin over 295 Kelvin, which means these kelvins will get cancelled and we will again get the units to be Pascal. And that turns out to be 8.43 into 10 to the power of 5 Pascal. Okay. Okay, let's move on to problem 3. So problem 3 is from chapter 3. Okay. Excuse me. A closed system undergoes a thermodynamic process. Initially, this system has a volume V and its temperature is T. During the process, the pressure of the system remains constant. Okay, so now this is a multiple choice question, and the question is, which of the following statements is correct regarding the system's change in internal energy. And we know that the notation for that is this. Okay, so I will give you a few parts, and again, I would request you to, as I'm writing the parts, I want you to think about what the correct answer should be, and then when I've written all the parts, pause, think, and then come back. Okay, so the first part is the internal energy, the change in internal energy is 0 because the pressure is constant. The second part is the change in internal energy is positive since the system is expanding. So this means positive, okay? If at any point you don't understand some notation, just feel free to drop me a message, okay? The third part says that the change in internal energy is negative since the system is cooling down. Fourth part, part D, says the change in internal energy depends on the specific heat capacity of the substance. And the last part says that the change in internal energy can only be determined if the specific heat capacity and the final volume are known. Okay, so these are the 4 options, and I would like you to pause and think which one's the correct. Okay, hopefully you've thought about it, and the correct answer is part E. Okay, so the question said that a closed system undergoes a thermodynamic process. Initially, the system has a volume V and its temperature is T. During the process, the pressure of the system remains constant. Which of the following statement is correct? The correct statement is that the change in internal energy can only be determined if the specific heat and the final volume are known. The change, so let me just write another statement. The change in internal energy of a closed system undergoing a thermodynamic process depends on both heat transfer, which is Q, and the work done, which is W. In this case, the process is not specified. So we cannot determine the heat transfer or work done without any additional information about the specific heat capacity and final volume. Okay, so this was a conceptual problem. In the finals, you will be having in the finals and in the midterms, you will be having a few of conceptual questions to answer, and I would suggest that you read your text perfectly. Okay, so let's move on to problem number 4. So this problem is from chapter 1. Okay, so it says truck brakes used to control speed on a downhill run do work, converting gravitational potential energy into increased internal energy. So this makes the temperature higher. Okay. Do increase internal energy of the brake material. Good. Okay. This conversion prevents the gravitational potential energy from being converted into kinetic energy of the truck. Okay. Since the mass of the truck is much greater than that of the brake material absorbing the energy, the temperature increase may occur too fast, or sufficient heat transfer from brakes to the environment. In other words, the brakes may overheat. Okay. Now, the question is, what is the temperature increase of 8 kg brake material with an average specific heat of 800 joules per kilogram times degree Celsius. If the material retains 15% of the energy from a 12,000 kilogram truck descending 55 meters in vertical displacement at a constant speed. Okay. So I would suggest you again to pause and then come back. Okay, now that you're back, I'm assuming you've thought about the question. It's an extremely long question, but you notice in the first half of the question is explaining you what the processes are taking place. Now that's very important, because if you note here, it says that the truck brakes used to control speed on a downhill run to work, converting gravitational potential energy into increased internal energy. And we will use this information and write down our solution. So let's first find out the gravitational potential energy. That is, we know it's mgh, and that comes out to be, so we have m, which is 12,000 kg. We have g, which is 9.80 meters per second square, or I think you'll be more familiar to this one. Yeah. And we have the height, which is 55 meters. Okay, since everything is in SI units, the answer will too be in the SI units, and the units for energy is joules. So the answer you'll get is 6.47 to 10 to the power of 6 joules. Now it says that this energy is converted into internal energy, and at the end you can see that it says, it asks you what is the temperature increase of 8 kg brake material with an average specific heat of this if material retains 15% of the energy from this truck. So we found the gravitational potential energy. Now we have to find the retention. So that's given by mgh over 15, because 15% is retained, and that just comes out to be, again, the answer will be in joule, 4.31 into 10 to the power of 5 joules. Okay, but that's not the complete answer. It asks us what is the temperature increase, and we know that the formula gives us Q equals change in the temperature mass times specific heat capacity. So if we want to find change in temperature, we just write this, and this gives us the answer of 67 degrees Celsius after substituting everything. Okay. Okay. So now we have problem 5, which is from chapter 2. Okay. Okay. So the question is a 325 grams piece of solid gallium. So what is a gallium? It's a metal that's used in semiconductor devices. Okay. So a 325 grams piece of solid gallium at its melting point of 30 degrees Celsius is in contact with 13.0 moles of air, assumed diatomic, okay, at 87 degrees Celsius in an isolated insulator. I'm sorry, in an insulated container. Okay. When the air reaches equilibrium, with the gallium, (213 grams of gallium has melted. Based on this data, the question is, what is the heat of fusion of gallium? And the notation is this. Okay. Now we are required to assume that the volume of the air does not change and there are no other heat transfer. So assume volume of air does not change and no other heat transfer. Okay, by now you know the drill. So welcome back, and the solution for this is, so first we need to remember, so recall that the heat transfer, when it's at equilibrium, we get the heat of the hot object and the cold object equals 0. This is when it's at equilibrium. Okay. Now, if you want to find a Q hot, we know the formula is N, and in this case, N is air, specific heat, and change in temperature. Okay. Where we just read in the question that it's a diatomic molecule of air. So CV is this. Q cold again is, so let's call this equation 1, call this equation 2, and Q cold is MLF. Now M here is the mass of the gallium, so to make everything explicit, I'm just going to write here GA. Okay, let's call this equation 3. Okay, now we just substitute equation 2 and 3 in 1. What do we get? We get N air CV delta T plus MGA LF equals 0. And what do we have to find here? We have to find LF. So we just substitute everything, and we know N air 13.0 moles, CV is 5/2. This is 8.31 joules per mole degree Celsius. And the change in temperature is 30 minus 87 degrees Celsius. I'm not going to write degrees Celsius. And then we have the mass, 0.325 grams. So it's 325 grams. We convert it to kilograms because we want to make sure that our every unit is in SI units. So let me just show this a little here. Okay. So this now is kg, and LF, this is what you have to find, is 0. So LF just comes out to be 447.34 kilojoule over kilograms. Okay, so that's your answer. Okay, so now we will do the last problem for today. Problem 6. And this one is from chapter 3. Okay. So the question is, the first law of thermodynamics establishes establishes a relationship between heat and work in a thermodynamic system. The question is, how does this law differentiate between the two forms of energy? So again, this is another conceptual question, and it has 5 parts. So part 1 says, heat is a form of energy. Heat is a form of energy transfer that is always positive, while work can be positive or negative. The second part says, heat is a form of energy. The second says that heat is a form of energy transfer that is always negative, but work can be positive or negative. Okay. Third part says heat is a form of energy transfer that occurs spontaneously. While work requires external forces. D. Heat is a form of energy transfer due to temperature difference while work is a form of energy transfer due to mechanical forces. And the last part is similar to this one that says heat is a form of energy transfer due to change in temperature or temperature difference. While work is a form of energy transfer. I think I missed, yeah, I'm so sorry. That's not the correct one. So the part E is heat and work are interchangeable forms of energy. And have same physical meaning. So now you have your question, give it a few minutes, think about which statement is true, and then come back. So I hope you gave yourself some time. Now you're back. So the correct answer is part D. Heat is a form of energy transfer due to temperature difference, while work is a form of energy transfer due to mechanical forces. So whenever you hear something like mechanical work done, you automatically know that there is something happening with work done. Some work is being done on a system. Okay, so that's for today. If you have any questions, you can just text me or mail me. Thank you. Bye.